Okay, so we can start. We were proving. Yes, so we proved convergence via Lyapunov argument, and I'm not going to write the statement, but I will go for the convergence of strongly smooth, of strongly convex and smooth. So the main result here for strongly convex and smooth, last time we have done only convex and smooth. Now we are doing strongly convex and smooth. So naturally the results, convergence results should be simpler, right? And that's the case here. So this theorem is, so we have f mu strongly convex and L smooth for some L greater than equal to mu greater than 0. Let xt be the sequence of iterates generated by gradient descent algorithm with a step size satisfying 0 less than gamma less than 1 over L. Then for x star, which is argmin of f, and for all t we have this bound xt plus 1 minus x star squared is less than equal to 1 minus gamma mu t plus 1 norm of x naught minus x star squared. Okay. So what this says is that this is the optimal solution here, and this is the one that is generated by the gradient descent algorithm. And if the learning rate in the gradient descent algorithm, okay, so gradient descent is just one line, right? X I plus 1, I put xi minus gamma grad f at xi. This is gradient descent. So if the gamma that you choose is between this 1 by L of the ellipsis constant, then the solutions as t increases, it's bounded by this. So if you look here, then x0 is known because this is your initial solution. X star is also known. This must be some point where the optimal achieves. So both are some constant. And if you look here, then this is gamma mu. Now gamma L is less than 1, right? Gamma L is less than 1, but then but mu is less than L, right? Or like L is greater than mu, so gamma mu must be less than 1. Okay, so gamma mu is less than 1 because of these two. So if gamma mu is less than 1, then this whole quantity is less than 1. Both cannot be, both are greater than 0 because both gamma and mu are greater than 0. And so gamma mu is between, from these two inequalities, gamma mu is between in the interval 0, 1. Okay, so that's clear. So we have a number which is between 0 and 1 and power t, right? So as t is increasing, number between 0 and 1 will keep decreasing and eventually become 0. Okay, so what eventually this is saying is that as you are running the gradient descent algorithm with gamma like this, then eventually you will converge to 0 because the right hand side will be 0. Okay, so that provides the guarantee that the algorithm converges. So when we look for convergence analysis, then the amount of contraction, right? So I call it contraction because it's something between 0 and 1. So it decreases by certain factor, right? So here let us say its gamma mu is like 0.1. So basically this means 1 by 10. So basically it means at every t it decreases the error by 1/10. Okay. The next time if I go, then depending on like what t is, right? So here I said just 1/10, but this is like 1/10 and then t plus 1, right? So as t is increasing, this is like, so at the next step it will be even more, 1 by 100. At t equals to 0 it's 1 by 10, at t equal to 1 it's 1 by 100 and so on. So this is the reduction in the this is the amount of reduction you are doing, right? So when you have an algorithm, how much reduction you do determines the rate of convergence. So if this guy was decreasing, but the way you so this is respect to the very initial error. Okay, so another way to see this is like xt minus x star, and this will be 1 minus gamma nu. Okay, so what this one is saying is compared to my current t plus 1, the distance from the optimal reduced by a factor 1 by 10 from the immediate last one, xt minus x star. So when I am looking for rates of convergence, then I am looking for t plus 1 and how much it contracted the previous one. So with this argument, this becomes our rate of convergence. So for this method, we will say that the rate of convergence is 1 minus gamma mu, and it is a linear convergence because there is no power here. Okay, if I look at the relative, right? So another way to say is like this. So this is less than equal to 1 minus gamma mu. So when I am deciding convergence rate, I look at t plus 1 and t, and this is a linear decrease. Okay, so the method, but here since I am recursively kind of applying the same thing again and again, then t plus 1 will show up here. Okay, if I keep substituting xt minus 1 x star as again with less than 1 minus gamma mu xt minus 1 minus x star, so each time you will get this 1 minus gamma mu. Okay, and if you keep doing backtracking, in fact when we prove this now, we will be here and then we will say that result follows by recursion. So so this decides our rate of convergence. When we look at the previous one, like if you see here, then you may say it's exponential, but it's not correct. Okay, we have to look into the immediate one, and then look at at this quantity which is linear. So now let us prove this theorem. We can prove this theorem with first order argument as well as second order argument. and both the proofs are small. So let us first prove with the first order argument. So we start from the left hand side, x norm of xt plus 1 minus x star is, so what we will do, since it's a gradient descent, in place of xt plus 1 I will substitute it by xt minus gamma grad f xt. So here I will do that. So then this is xt minus x star minus gamma grad f xt. So I have just what I have brought in, what I have put in place of xt plus 1 is xt minus gamma f xt. That's the gradient descent, right? Okay, then we will expand on this. So this is a square here. So we will apply the a plus b whole square formula here. So this is xt minus x star whole square minus 2 gamma inner product of grad f xt comma xt minus x star plus gamma squared of the b square, which is grad f xt squared. Now we have to do the upper bound here. Upper bound, I did some calculation. It took a little bit of figuring out. So without wasting your time, I will do this. So we have this. Okay, so from now next step is to use the strong convexity. Remember that we are looking for upper bounds, right? We are always looking for an opportunity to make it less than equal to. And we are given that f is mu strongly convex, so we will try to use that now. So from strong convexity of f with, so we will invoke the strong convexity with the strong convexity formula involve y and x. So in place of y I will put y equals to x star and x equals to xt. Then we have fx star minus fxt, and this is greater than equal to grad f xt x star minus xt plus mu by 2 norm of x star minus xt whole square. I have just written the convexity argument, which was fy greater than equal to fx plus grad fx y minus x. So I have written exactly that. It's just that the fx term is now here. So this is like fy minus fx is greater than equal to this. So this is just a strong convexity definition, right? If this term was not there, it was pure convexity. But in strong convexity, we also have this term now. So this is mu strongly convex given. Now from there, the idea is that you figure out an upper bound for this from here. Okay, so I will rearrange things in a way that minus 2 gamma or minus of this is less than equal to something. Okay, so that's my plan. So let us do that. So minus I need, and if I do a minus, then yeah, minus I need, but then there is a what I need here is xt minus x star, but here is x star minus xt. So another way to do is like I take a minus from here, and then it becomes exactly in this form, xt minus x star. So basically I take a minus here, and this minus of this, basically this minus of this quantity, this you can forget 2 gamma, this is less than equal to something, right? So that way also I can use, right? And mu term is also there, right? So let us do that way. Okay, so what I will say is that minus of this guy, okay, and I will bring it here, and I won't change the inequality also, and I will move this guy here. So let me do that, and then you can figure out. So what I'm saying is minus grad f xt, and I flip this. That's how I got the minus here. So then it became xt minus x star, because I'm looking at this, okay. So I'm bringing in that form, and this is less than equal to f, and yeah, let us write it that way. So fx star minus fxt, and minus, okay, I moved this guy there, so it became minus mu over 2 norm of x star minus xt whole squared. So I can substitute this now, and 2 gamma is there for sure, so that will get multiplied. So this would mean that minus 2 gamma of this is less than equal to minus so here it will be like, yeah, just 2 gamma of this, and then 2 gamma here, okay. So let us replace that, okay. So let us replace this guy. Looking at the number of lines, let us say we do it here, okay. So now I will just copy that xt term there. So xt plus 1 minus x star, and I will now directly say this is less than equal to, and using this, okay. So now this guy is less than equal to norm of xt minus x star whole squared minus 2 gamma of this guy, which means 2 gamma of this guy. So is less than equal to minus, no, minus is already taken care of, so this will be now plus 2 gamma of fx star minus fxt okay, and then minus 2 gamma, okay. So 2 gets cancelled, right. So then minus 2 gamma mu by 2, and then x star minus xt. That's the red one we have completed. So the red one corresponds to this term here, which we have just now substituted, and then we copy over that term plus gamma square norm grad fx squared fxt squared. So something common seems to be there. X star minus xt or xt minus x star both are the same term because they are in the norm. So this will be equal to 1 minus gamma mu norm of xt minus x star, that I have taken common now, and then we have the remaining terms, and we are supposed to use some intermediate results on the grad f also. So I have to recall that now, which is the lemma that we proved before, that will give a bound on the grad f. All right, so I can do it immediately maybe. So this is plus, I would prefer to write it as fxt minus fx star, so I will take a minus common here. So minus 2 gamma fxt minus fx star, and this guy is, we have done this before as a lemma. So now this becomes, so I will write this and then I will cite that lemma. Okay, so this will become 2 gamma squared L f x t minus infimum of f. So this thing is from a lemma that we did before, and this was this lemma was 1 by 2L. So this was like the smoothness lemma, consequence of smoothness, fx minus infimum of f. Okay, and this should have been applied on the whole of this. Okay, so grad fxt is less than equal to fxt minus infimum. So 2L goes there and gamma was already there, gamma square was already there. So we also have now fxt and fx star common, right? So let us now simplify it further, and this became further less than equal to, okay, because of that lemma. Now we can simplify this. So this is 1 minus gamma mu norm of xt minus x star squared minus 2 gamma and 1 minus gamma L and fxt minus infimum of f. Okay, so we just simplified this now. Now let us look into this. So since 1 by L is, so gamma is less than or equal to 1 by L, the claim is this guy is negative. So gamma being less than 1 by L means gamma L is less than 1. Gamma L less than 1 means this quantity is positive, gamma is positive anyway. So overall this is surely a negative quantity. So if this quantity is negative, if I drop the negative quantity, then it will be less than or equal to this. Okay, so here gamma is less than 1 by L, that is gamma L is less than 1. This implies 2 minus 2 gamma 1 minus gamma L is surely less than 0. Hence dropping the second term. So we drop the second term and we still get this less than or equal to 1 minus gamma mu norm xt minus x star. So as you can recall, this is what essentially we wanted to do. But if we now apply this recursively, then we will get to x naught, and each time one factor will pop up here, and if we go until 0, then t plus 1 of these will pop up. Okay, so using recursion, I have 1 minus gamma mu t plus 1 is less than or equal to now x0 minus x star squared. Okay, so we make a box and then fill it. That means that it's done. Okay, this theorem. So this is when we have strongly convex and L smooth. Then the proof goes like this. We can also prove this via second order information, which is the Hessian, and obviously their eigenvalue will play a role and fixed point iteration will be used there. So let us try to do the same proof but using second order approach. Okay, so proof with Hessian. So Hessian means grade square f, like second order derivative of f. So let T from Rd to Rd, and let us say that T is x minus gamma grad fx. By looking at T, you can say that what T is doing, right? T is doing a gradient descent step, right? And I am seeing this gradient descent step as an operator now, operator T, right? You give me an operator, you give x to the operator, and it does one gradient descent step for you. Okay. Essentially, we are going to some fixed point iteration idea, but let us use these notations first. So with this notation, the gradient descent becomes, so the gradient descent is xt plus 1 is t of xt, right? So xt plus 1 is t of xt, meaning xt minus gamma grad of xt. That's exactly the gradient descent, right? So if there is a minimizer of a function f, right, at the end of the day, we are trying to do the minimization problem of fx over x. Okay, this is what we are doing, right? And if there is a minimizer, then grad fx should vanish, right, at the minimizer. So for minimizer x star, we have grad fx star is equal to 0. That is like well known. In that case, that x star will become a fixed point of the operator T, because in that case, grad f at x star, grad f star is 0. That means T x star is x star, and that is exactly the meaning of fixed point. A point x is a fixed point of an operator if Tx is x, right? So this characterizes the fixed point thing of T, right? So this implies, so this implies T of x star will be x star minus gamma grad f x star, but at f x star this is 0. So this implies T of x star is x star. This implies x star is a fixed point of the operator T. Fixed point methods are the most generic framework to study iterative methods. You can also study this in generic spaces, okay, very generic spaces, Hilbert space, Banach space. You have big books written just on fixed point on Hilbert space, fixed point on Banach space. Just fixed point methods also, if you search on Amazon, there is a whole set of theories just on fixed point methods, convergence, and so on. So we are having an initial taste of these things. So we want to have a fixed point view of an iterative method. Most iterative methods have underlying fixed point. Even if you study so-called RL, if you go into the theory, there are fixed point. You have to show that there is value iteration or whatever iteration you have, Polish iterations, you have corresponding fixed point operator, and for that to converge, you have to show that you have to arrive at certain fixed point. So for the moment, we will go into fixed point in more detail later on. But for this proof, let us stick to what we have right now. So okay, so this is a fixed point, and if this is the case, then we can also write this means that xt plus 1 minus x star is can also be written as, because so xt minus tx star. Okay, I can do that because x star is tx star, the second term is fixed. Is that right? Why this means that xt plus 1 was t we just wrote, right? That's the point here, right? So we have a and you have b. A and b combined gives me this. So in place of xt plus 1 I introduce txt, and in place of x star I have tx star. Okay, so we can write like this. Now we want to prove that norm of txt minus tx star. So essentially this is what we want to bound, right? We want to see how far is our iterate from the optimal, and this boils down to this. So essentially we want to bound this now. Okay, so this is, we want to prove that this is less than equal to 1 minus lambda mu norm of xt minus x star. So you can see this as xt plus 1 minus x star is less than equal to this, which is exactly what the theorem was asking, right? But the fact that we have introduced the operator t now, this will allow us to use the properties of t. Okay, so somehow related to eigenvalues. Okay, mu strongly convex, right? So you have smaller eigenvalue bounded by mu and larger eigenvalue dominated by L. So all this will play a role now. Okay, so so the next step is if t happens to be Lipschitz continuous, right? In the sense that the constant, the Lipschitz constant of t, if it happens to be like this, then we have immediate result, right? So there is nothing more to prove. If t happens to be Lipschitz continuous with L being 1 minus lambda mu, then it's a straightforward proof, right? So let us write this as equation C. So we see that C holds as long as t is theta. Let us say that constant is theta. Okay, so theta Lipschitz with theta being equal to 1 minus lambda mu. A result that we did before is that if a operator or a function is theta Lipschitz, then it's equivalent to saying that the norm of the derivative of t will be bounded by theta. Okay. So being Lipschitz means the gradient is bounded, right? So we have seen that result before, right? So this is equivalent to proving. So I mean it cites lemma 2.6, but that's exactly the lemma we are supposed to use. Okay, so for the sake, maybe I can rewrite the lemma. Yeah, so this was the lemma in here. It's like lemma 2.6. So recall lemma. So f rd to rp differentiable, and f is L ellipsis, then d of f is less than equal to L. Okay, so this is what we are trying to recall. So if t, in place of t we have f here, right? So it's like capital F, let us say. So if t is theta ellipsis in our case in place of L, then the gradient of t will be bounded by theta in our case. Okay, so let us now go back. Okay, so we first need to take the derivative of t. So t was defined to be x minus gamma grad f, right? So if we take the derivative of that, so dt in our case is, so derivative of x is identity, right? So with respect to x is identity, and then minus gamma and grad square fx. So this is our derivative, and so this will be bounded by theta, right? Now let us extract the eigenvalues of dt, because the norm of this will be the largest eigenvalue of t, right? We have also seen this before. So for completeness, let us write down these details. So if let v1 let v1x v2x dot so this is less than equal to, okay, v dx. So these are the eigenvalues, okay, are eigenvalues of grad square fx. The reason why we put x is that the eigenvalues will change from point to point, right? At different x I have different Hessian, so eigenvalues are dependent on x, right? So let this be the eigenvalue, and eigenvalues are ordered, okay. So what we have seen also previously is, then in that case the VI's, the eigenvalues are bounded by the mu, which is the smoothness, and by L, which is the mu, which is the strong convexity, sorry, and L, which is the smoothness. Okay, so the eigenvalues lie within this, right? We have also shown this before. Okay, so this is the bound on the eigenvalue, and obviously if you look into dt, so dt eigenvalues lies between 1 minus what are we supposed to get, right? Lambda mu. Yeah, what we have written are the eigenvalues of gamma, and I have to kind of subtract 1 from both sides. So I mean we have written eigenvalue of this, right? But what we want is eigenvalue of this. So eigenvalue of this will be, given that eigenvalue of this are known Vi, then eigenvalue of this will be 1 minus gamma Vi. Okay, so I can write this as eigenvalues of, let us say eigenvalues of this is written by lambda I dtx. Then these are nothing but 1 minus gamma Vi x. Can you show about the bounds of these eigenvalues of dt, right? If the VI's are bounded between mu and L, what about lambda I of dtx? Okay, if VI's lie in the range mu and L, what about this? It's a simple inequality, right? So maybe we are lazy in the evening, right, to do all this, but so this would with this we will have lambda Vi lying between 0 and, so this implies 0 less than equal to 1 minus lambda Vi x and this is less than equal to 1 minus lambda mu, and we have also assumed that the lambda L is less than equal to 1. Okay. So with all this, we can show that 1 minus lambda Vi will lie between 0 and 1 minus lambda mu. From here, what do we get? If we look into the fixed point iteration and so on, right? First of all, what we see is that dtx, right? The norm of this is bounded by 1 minus lambda mu. Okay. So now we can conclude about the norm that I said just now. So dtx, the norm is, so since this is a norm, the norm will pick the maximum of the eigenvalues. So this is max of I equal 1 d, okay, and 1 minus lambda Vi x, and this is less than equal to 1 minus lambda mu, which is theta. Right. So we have the norm which is maximum of the eigenvalue. Norms, not all norms are maximum eigenvalue. The 2 norm is the maximum of the eigenvalue. So in this case, we are considering 2 norm by default. So this is the maximum of the eigenvalues, and then all of these, the maximum they can go is 1 minus lambda mu. So I replace that maximum by 1 minus lambda mu, and if it so happens that, so this is what we started with, right? So theta is 1 minus lambda mu. So then C holds, right? Is it given in the question that lambda less than equal to 1 is given, right? Lambda is less than 1 by L is given. So lambda L will be less than equal to 1. So the fact that T is theta ellipsis is coming from the fact that this was given that F is L ellipsis. Okay, this F is L ellipsis. T is just an operator that we created out of F. So F being L ellipsis was given to us. F was mu strongly convex was given to us. We formed an operator T out of this, which is an operator corresponding to the gradient descent. And then the fact that F was L ellipsis, it implies that T is theta ellipsis, with theta being this. This is what we proved just now. And the very fact that theta is T is theta ellipsis with theta this exactly means this, and this exactly means this, right? So meaning x, so this was this, right? So meaning that xt plus 1 minus x star is less than equal to this, which is what we wanted to prove, right? So this is another way to prove, but then here what you needed was second derivative. Okay, you needed second derivative. So this is another way to see things, right? How things are related also to eigenvalues. Okay, in other words, what all this is saying is that that the function that you are trying to minimize, okay, if that function eigenvalues are lying between mu and L, okay, and your step size is such that lambda L is less than equal to 1, then you are guaranteed to converge. So things are also related to eigenvalues of F. F being mu strongly convex means mu is the lower bound on the smallest eigenvalue of F. F being L smooth means that L is the upper bound on the maximum eigenvalue of F, and your step length, if it is less than equal to 1 by maximum eigenvalue of your Hessian, the function that you are minimizing, then you are guaranteed to converge. Okay. So another way to see is, the only problem is from practical point of view, it's not so I mean, from theory it's look good, right? But computing the maximum eigenvalue itself may be more costly than doing gradient descent. So in theory it looks good saying that my largest eigenvalue is bounded by L, but to have an estimate of L is like finding the maximum eigenvalue, or you may have some rough estimate that will also work, but that rough estimate may be very bad also, right? But yes, so that's how the eigenvalues are related and help in the convergence. So we can prove, we have seen PL condition, right? And we have not proved any convergence yet for the PL, and the proof is easy. So let us do for PL, okay, which PL means it may not be convex, so it's a slightly generalization of the convex, and yet it guarantees convergence. So convergence for PL and smooth. So here it can handle non-convex, but those non-convex are PL, right? So non-convex is possibility now, but PL. What is important to note for PL is that their minima is also global minima, although they are not convex. So you can think of functions like this. So okay, these are likely to be PL. They are not convex, but they have a global minima. Okay, because at these places gradient is not becoming flat. Okay, it's becoming flat here. So these kind of functions are extension of the convex functions, and we can prove convergence guarantee for this class. Okay, so this is what we are trying to do here. So these are possibly non-convex, but has to satisfy PL. All local and critical points. So the fact that you have PL, it still guarantees that all local are also global. Okay, so all local minima and critical points are also global. I guess we have proved this. If not, you can also try that. Also global minima. Okay, so this is the setting we are looking at now. So far we were into the convex regime. Now we are slightly going ahead with the non-convex, slight extension going on now. Okay. So a main result that we are supposed to prove in this case is the convergence guarantee is this theorem. So sometimes it's good to write the theorem number in the notes. Notes are uploaded in the Moodle in the references tab. Okay, so let F be mu PL satisfy B mu PL and L smooth. Okay, we still need the smoothness also. For some L greater than equal to mu greater than 0, then let us say we generate a sequence via gradient descent. So gradient descent, guarantee of gradient descent for PL. Okay, so let the sequence be generated by gradient descent. So consider xt t in natural number a sequence generated by GD algorithm with a step size satisfying zero less than gamma less than 1 over L. Then the guarantee is that fxt minus the infimum of f is bounded by 1 minus gamma mu to the t f x naught minus infimum of f. Okay, so in this case, we are saying that the xt that the gradient descent is producing is such that its difference from the lowest value is decreasing as t is increasing, because gamma mu is less than 1, mu is less than L, so and gamma is less than 1 over L, so gamma mu is less than 1. So gamma mu is less than 1 and greater than 0, so hence this quantity is less than 1. This quantity is between 0 and 1. So then if I raise to power t and t tends to infinity, that's definitely going to 0. And fx0 and infimum of f, these are constants, because once I fix an initial guess and minima of a function is fixed, so these guys are constant, so they will not change with t. So this is the guarantee that we want to prove, okay, for the PL case. So let us try to prove this. We are supposed to use lemma 2.25 together with update rule. Okay, let us recall 2.25. Yeah, that's the smoothness basically for a differential function, right? So I will just recall this lemma. So recall that f from Rd to R is L smooth, then for all x y in Rd, fy is less than or equal to fx plus grad fx y minus x plus L by 2 norm x minus y whole squared. So this is the L smoothness. We have just copied it and update rule of the gradient descent we know. So now let us start with f x t plus 1. Now this is less than or equal to, well, this is essentially this guy itself, but in place of y where I'm using t plus 1 and so on, and in place of x I use xt plus grad f xt xt plus 1 minus xt plus L by 2 xt minus xt plus 1 squared. So we started with L smoothness, y is xt plus 1 and x is xt, and we would apply the gradient descent here, and we will bring out the norm grad f xt squared, because xt plus 1 minus xt according to gradient descent will be minus gamma grad f xt. Okay, that's what we know, right? Because gradient descent is xt plus 1 is equal to xt minus gamma grad f xt. So hence we can write that, and that will allow us to have grad f xt norm there. And what can we do for the second term here? Oh, second term also we will invoke the gradient descent. So this will also be grad f xt, okay, or minus grad f xt, same argument. So then we see norm grad f xt squared, here also norm grad f xt square, and we take the constants together. So let us do this. In the first step we do this norm. So minus gamma I took it out, and this is norm grad f xt squared plus L by 2, and there is gamma also here. So L by 2 gamma squared, because here is a norm squared here. So gamma squared, and then grad f xt term remains here, right? Squared. Now we will take this grad f xt common, obviously, right? So this is f xt minus gamma by 2. Okay, let us write down and then we will see. So gamma by 2, 2 minus L gamma, and norm of grad f xt squared. Okay, it seems to be okay, because if I multiply this back, then gamma by 2 times 2 is gamma, and then plus L gamma square, that's fine. Okay, so so what about 2 minus L gamma, right? Is this can we get rid of that, right? So L gamma is less than equal to 1. L gamma, so what we had is gamma less than equal to 1 over L. So L gamma is less than equal to 1, and both these are greater than equal to 0 for sure, right? So minus L gamma is greater than equal to 1, and greater than equal to minus 1, right? And then I add the 2, because I'm looking into this whether I can kind of drop this. So this is like 2 minus L gamma is greater than equal to 1. Okay, so 2 minus L gamma is greater than equal to 1, meaning if I drop this guy, and since it's a negative, right? So in other words, if I multiply by negative here, so 2 minus L gamma is less than equal to 1. So I use this fact that minus of 2 minus L gamma is less than equal to 1. So I substitute minus of 2 minus L gamma by 1. So then I get less than equal to fxt plus, because minus 2 minus L gamma less than equal to 1. So this is like plus gamma by 2, and then norm of grad f xt squared. Or there is a minus 1 on the last step, right? Yeah, I took a minus 1 again. In that case, what do I do? I replace, yeah, so this is minus 1. It remains minus then. Right. Yeah, so this was our first step, where we have this bound on fxt, because eventually what are we supposed to get? That one, right? Fxt minus infimum is less than equal to, okay. So here comes the PL step, right? So far we have not used the PL step, and PL step was a bound on this, which also involved fxt minus infimum. So that's where things will get sorted out now. Okay, so we will apply the PL. Okay, now recall the PL condition, which was f from Rd to R and differentiable mu greater than 0, and this implies fx minus infimum of f is less than equal to 1 by 2 mu norm of grad fx squared. This was the PL condition, right? So if we apply that, we want to get rid of that grad fxt, right? So we need a negative of that. So negative of that will be less than or equal to fx minus infimum, and obviously there are constants involved. So we will try to so this is like 1 or 2 line more. So negative of this is less than equal to, so negative of 1 by 2 mu grad f x squared is less than equal to negative of that, right? So negative of fx minus infimum of f, because we are looking for the upper bounds, right? But then we have, okay, what we have, so minus, and the minus will remain there, right? Because I am going to replace this, so there is already minus here, so minus of grad f xt squared will be less than equal to minus on the right hand side, right? So let us now go back to this fxt plus 1. Now this is less than equal to fxt and minus, and gamma by 2 will remain. Yeah, gamma by 2 will remain, and then 2 mu will get multiplied, right? So it's like 2 mu and gamma by 2 remains, and these all this is less than equal to, and then there is another negative, right? Minus of fx minus. So all this 2 gets cancelled, minus minus becomes plus, right? So we may try to, okay, let us first write and then we'll see. So xt plus 1 is less than or equal to fxt minus gamma mu. Yeah, well, we can make it plus, I guess, and we have x naught first, right? So that seems to be in a good shape, right? So let us say plus, and then fx, I think it was fxt, right? So we have to put xt everywhere. It's fxt minus infimum of f. And it is not yet in that form, so the additional thing I see is infimum of f. So I subtract infimum of f both sides. So subtracting infimum of f both sides will give me the result, right? So this is fxt plus 1 minus infimum of f is less than or equal to infimum, right? So 1, that should we are getting plus, right? But ideally we are looking for minus. We are looking for 1 minus gamma mu, and what we are getting is 1 plus gamma mu. So we have missed some minus plus somewhere. In the PL condition, fx minus infimum of f. So the PL condition is fine, there is no problem. What did we do here? This was negative, right? If I check here, this was also negative here. So this seems to be fine until here. And after that, we have PL condition, which is fine. So then we have fxt plus 1 less than or equal to fxt minus, so minus, I don't want to change. Okay, there is something we might have done here. Fxt minus get fxt square I wanted to replace and that was already taken care of, right? Because I had a minus here, or I removed this minus, right? That was the mistake. So then we have this minus. Okay, so we are back to track. So fxt minus infimum of f, and okay, we take that common already, right? So since I am subtracting by infimum, then 1 minus of that, right? So 1 minus gamma mu, and then fxt minus infimum of f. Okay. So this is what we were supposed to prove, and we have to do it recursively now. We have to now substitute this again. So fxt minus infimum of x is less than or equal to 1 minus gamma mu, fxt minus 1 minus infimum of x. So if you keep doing this recursively, so doing recursively, I will get eventually gamma mu t plus 1. Okay, in this case is t. Okay. Okay, so it's t, and then fx0 minus infimum of f. For PL condition also we have this guarantee, right, that it will converge. but this t is okay, right? Should be t plus 1. Oh yeah, sorry, because this is with t, but here we are running with t plus 1, right? So there should be one more extra term here, right? Or if you want, you can reduce it to t here, then it will be t, right? So I want to go to the also some stochastic regime. You see, we have not done any stochasticity here. In practice in machine learning, we use stochastic gradients, right? We have done one proof, which was a tricky one. I told you that I will tell you another proof. So my goal is to show that proof. So what I will do is that I will take like maybe 10 minutes and just define few things like expected smoothness, expected mu strong convex. Okay, so I will just change what we did in expected. Okay, so then we will handle because gradient will be a stochastic gradient. So then everywhere we have gradients, we have to write expected gradient, right? So that's where, because as we have seen also in like previous morning class, right? When you were training the generative model, GAN, right? You were taking batch of the samples, right? You don't take the full data. So since your loss is on the small number of data, your gradient is partial gradient, not the full gradient. Okay, so that means that it's a stochastic gradient because you also pick these samples randomly. Okay, and then in that case, the analysis will go with the fact that gradients are random variables then. Okay. Okay, so I will do this little bit of this. I will not start any proof today, just basic definitions, and then for today I will stop. Stochastic proof I will do next time. So there are few things for sum of functions, because if you see in machine learning, what we do is we are essentially dealing with sum of functions. So h theta of xi minus yi. Okay, so this is typically a machine learning problem where the loss function is defined to be like this. Okay, and we are supposed to minimize. So one of the specific cases of functions that we should look at are the sum of the functions. Okay, here we have not considered those specific cases. Here we have studied in general, f could be any function, right? But in machine learning, what is needed are these specific cases where I am looking at the sum. So your analysis can be made more specific to these cases. Okay, so these are some like fi, okay, and that you are summing. So that's what I am going to do here. Like I will define few things about sum of functions. So we want to minimize a function f from Rd to R, and where f is seen as a function of this fix I equal 1 to n. Okay, we call this sum of functions, where fi's are multivariable but real valued, and we require that problem is well posed. In the sense that argmin of f is not empty. So it's well posed in the sense that there is some minima there. Okay, it should not be that its minima is not there. Okay, so and that fi's are bounded. Okay, so we are like expecting these things. So as a specific case, we can also consider functions which are sum of convex functions. Okay, so one of the assumptions we can do is sum of convex. Okay, So here each of the fi's above are convex. Okay. This is further special case. We may also look into sum of L max smooth. So now we want to see whether this each fi have some L smoothness. Okay. Then we can talk about maximum of all the L's of fi, or we can talk about the average of the L's of all fi. So these are the specific cases. So for instance, sum of L max smooth. So in this case, assume that fi rd to r is Li smooth. Okay, so each of the fi's are Li smooth, and in that case, since it's a sum, each are L smooth, so we can take a max of all the L. So as a whole, it will be L max smooth. So f will be as a whole L max smooth, right? So we can create a L max, which is defined as maximum of Li, and we can also define L average, which is by definition average of all the Li, Lipschitz constants. So if the fi's are L smooth, then the given function is L max smooth or L average smooth. Okay, so that's the consequence. It's not like assumption, right? So this is what this lemma like clearly points out. So if fi's are Li smooth, then f is L average smooth. So the proof is very simple, right? So grad f y minus grad f x. So since each of these fi's are sum of the functions, then the gradient will be sum of the gradients. Okay, and so n by n is basically for both. So n by n, 1 by n can come out, and then we apply ellipsis on each of the fi because they are given to be ellipses. So we can write that 1 by n and sum of each fi are the sum, right? So there will be mixed terms maybe then. We may have to use triangular inequality then, right? So each of the f so if I write this as a first step, let us say, and then so by definition each of these are sum of 1 by n grad fi y, and then minus 1 by n grad fi x. Okay, so fy is a sum, and then fx is a sum, right? And from there we are supposed to 1 by n can come out, that's fine. We can take the sum common, that's one thing, and then norm goes inside, right? That's the triangular inequality. Sum can be combined, right? So let us take 1 by n out, and this is sum of grad fi y minus grad fi x. Sum we took it out, right? I equal 1 to n. So far it's an equality. So this sum is applied on the whole, and this is like norm of x plus y is less than or equal to norm x plus norm y, right? But in this case it's like there are many Here we have x, but here it's like 1 to n. So it will be less than equal to each of these i's. Okay. So basically norm goes inside and sum goes outside. That's the triangular inequality, right? So this is less than equal to 1 by n, sum goes out. Wow, I mean these days phones ring a lot. Yeah, so the sum goes, the norm goes inside, and we have grad f I y minus grad f I x. We have to show that f is L average, right? But fi's are L smooth, right? Li smooth, right? So I can replace these by L of y minus x. No, y minus just L, right? So this is like less than equal to, because it's grad, right? So this is less than equal to sum of Li. Since grad fi are Li smooth, right? And this is indeed the average of Li, right? This is, oh, this is smooth, sorry, not continuous, right? Yeah, this is smooth. So here we will have norm of y minus x. If it's continuous, then we have just the bound on the gradient, but if it's smooth, then we have L times norm of the y minus x. Okay. Right. So we can replace the, because y minus x is common for all, so that goes out, and then I can just put this into brackets. So this is nothing but L average norm of y minus x. Now max also you can do, that's fine. Okay, so okay, I will stop here for today. Okay, the stochastic variant we will start. So far we have not touched stochastic so far. Okay, so from the next class we will do.